Hello, Prof. Mo here of chemjoint.com. I will be discussing the structural factors that affect acid strength or even base strength. We will be focusing on acid strength based on the most acidic hydrogen on the molecule. That will help us to determine which molecule is stronger than which molecule when given maybe two or more molecules to rank the acidity. The factors below affect acidity or even basicity. We go with the acronym ARIO. A stands for atom, R stands for resonance, I stands for inductive effect, O stands for orbital type, which goes with hybridization. I've not written them in order, but the most common ones will be atom and resonance stabilization. These factors will tend to stabilize what we call the conjugate base. And we'll say the weaker the conjugate base, the more stable it is, the more likely it's going to be formed from an acid-base reaction, which in turn dictates the strength of the parent acid that lost the proton to make the conjugate base. That's the basic idea we'll be using. I have here a sliced cut snippet of a periodic table, the right hand side of the periodic table. Generally, electron affinity, or what we call electron wanting tendency, or what we call electronegativity, increases from the left to the right of the periodic table and from the bottom to the top of the periodic table. So fluorine becomes the most electronegative. So this will help us to determine acidity. Okay. Generally, acidity in the periodic table increases from the top left to the bottom right. Okay, and then the opposite will be for basicity. We'll talk about such factors. Let's go step by step. Let's discuss factor number 1, atom. How does the atom affect acidity? Let us consider the atom factor and acidity. So let's assume that we have a CH4. Let's assume we have an NH4. Let's assume we have an NH3. And then we have H2O. And then we have HF. So I will rewrite this this way. I will rewrite this as CH3 exposing a hydrogen from it, NH2 exposing a hydrogen from it, and then HOH exposing a hydrogen from it, and then HF. The reason why I did this, I want you to see where the hydrogen is bonded. Okay. The factors we're going to consider here are those atoms that are bonded to the hydrogen. So in this case, we have C, N, O, and F. Let's talk about acidity. What's an acid? Something that donates a proton. So let's assume we have a strong enough base to take out that hydrogen. What we will end up with is conjugate base with negative on the carbon, and of course we're going to end up with the conjugate acid. Okay. For the next one, we do the same thing. We take a prototype base strong enough to take out that hydrogen. You'll always end up with a conjugate acid and a conjugate base. We discussed this in an earlier lesson. And then we do the same thing. We take out that hydrogen. We're still gonna end up with a conjugate acid on the product side and the conjugate base. We do the same thing. We bring up a base that can take out that hydrogen from the acid. Acids are proton donors. you still end up with the conjugate acid and the conjugate base, which in this case is F minus. Now you see why I was listing this, because those are the ones that are carrying the negative charges, you see. So which of these is the most electronegative? Fluorine is the most electronegative. Fluorine is most electron wanting. The fluoride will hold the electrons tighter than the carbon. And that means this F minus is the weakest base. The conjugate base here is going to be the weakest base of all, because remember, a base should be a species that is easily electron donating, but because fluorine is more electron wanting, it's mean, it holds on the electron more tightly. So it's the weakest base, and if it's the weakest base, it must have come from a stronger acid. Weak conjugate bases always come from stronger parent acids. So HF here is going to be the strongest acid compared to what we call methane, because after it loses a hydrogen, after the HF loses a hydrogen, it makes a fluoride which is stable, meaning the electrons are tightly held, electrons are comfortable on it. Okay, so if I'm to rank acidity, CH4 is going to be less acidic than NH3. NH3 will be less acidic than water. Water will be less acidic than HF. And that's why we are saying the tendency of acidity goes basically from the left to the right, or overall from top left to bottom right. Okay, so we are considering elements in the periodic table that are on the same row. We can consider electronegativity. The more electronegative the conjugate species is, the more acidic the molecule, or the hydrogen sitting on the molecule. So that is atom example number 1. Okay, so it's very important to consider the atom type, and this one, remember, when we are going across the periodic table, we consider electronegativity and atom type. The more electronegative the element is, the weaker the base it is. It must, when protonated, it must form a stronger acid. Okay, let's look at another example. Since we've shown an example of going across the period, let's talk about elements in the same column. When you're looking at acidity or comparing acidity of elements in the same column, you don't consider electronegativity, you have to consider size. And I'll show you 2 examples. So let's say we want to rank HF versus HCl versus HBr. I'm choosing halogens, main group 7, versus HI. Now, like we said before, when these react with a base, you'll get conjugate acid and you're going to get the conjugate base. Similarly, in the next one, you react it with a base, take off that hydrogen. Bases are proton acceptors, acids are proton donors. You'll get the conjugate base, conjugate acid, and the conjugate base Cl minus. Similarly here, you get conjugate base, which is Br minus, when the base takes off that hydrogen, and you will get conjugate acid. Similarly here, bring a base of whichever type. B is just a prototype base. Any base strong enough to do this. Okay, you get a conjugate acid and you're going to get a conjugate base. Now, I said that we have to consider size. Who is the biggest? Remember, as you go down, size increases. iodine is gonna be the biggest, okay, which means there's more room for electrons to reside in the anion of I minus compared to the anion of F minus. Size. So electrons here have more room to delocalize and, polarize the anion. So because there's more room, I minus is gonna be the weakest base. And remember what I said. If you are a weaker base, when protonated, you must form a stronger acid. So in terms of acidity, HF is less acidic than HCl, HCl is less acidic than HBr, HBr is less acidic than HI. So I'm comparing the extremes, then we do the ranking. Let's do another example. Example number 2. Let us rank H2SE versus H2S versus H2O. Which one is the most acidic? Of course, if you know which one is most acidic, the opposite you get, which one is more basic. So what we'll do here, I will do like I did before. I will have to expose a hydrogen out of this. Expose a hydrogen attached to the more electronegative element. Expose a hydrogen. So again, the elements you're comparing is Se, sulfur, and oxygen. They are right here in main group 6. They are on the same column, so I have to consider size. I will tell myself if I have a base that is strong enough to take out this hydrogen, because bases accept hydrogens, I will get a conjugate base. I will get a conjugate acid, conjugate acid, and I will get a conjugate base that lost the hydrogen. So similarly here, if I have a base enough to take out that hydrogen, I will get the conjugate base of sulfur, but I will also get the conjugate acid out of the reaction. Same thing here. Now you know the drill. Take out the hydrogen, acid-base reaction, you'll get the conjugate acid out of the reaction, and then you get the conjugate base out of the reaction, which is the hydroxide. So what I want you to compare is the anion, the Se, the sulfur that's negatively charged, and the oxygen that's negatively charged. Who is the biggest? As we go down, you're increasing atomic number. You are increasing the number of shells on the structure of the atom and an ion, and so you're increasing the atomic radius, you're increasing the size. So out of this all, this is the biggest because size increases going down. So Se minus is likely to accommodate the negative charge easier than OH minus. So this one will be the weakest. This will be the weakest conjugate base. We are judging the strength of the conjugate base and using that to determine the strength of the parent acid. So the weaker the conjugate base, the stronger the parent acid. So H2Se is more acidic than H2S, which will be more acidic than water. That's the idea. This one will be the strongest base because the electrons are more exposed, because oxygen is smaller. So the parent acid will be the weakest acid of them all. Okay, that's the idea. Let us look at another factor. Having talked about ARIO effect, let's talk about resonance. If the conjugate base from the reaction, acid-base reaction, is more stabilized by resonance, then the parent acid will be stronger. Let's do two cases. Simple example, let's compare acetic acid, okay, versus ethanol. which is beer. Question: which of these two, without looking at pKa numbers, which of these two is more acidic? So you will do the same thing. You will tell yourself, suppose, so this is example 1. Suppose we give this a base. And the base here could be something, e.g. OH minus, So I'm just using B as a prototype for base. So the base will take out the hydrogen. We did this mechanism before in an earlier lesson. And then you get an acetate. So negative charge goes on to the oxygen. We did that in an earlier lesson, calculating formal charges. You get conjugate acid and conjugate base, the acetate from acetic acid. Okay, do the same thing with ethanol. Suppose you have a base strong enough, because not all bases are going to deprotonate the ethanol. So you're still gonna get a conjugate acid, and you're gonna get conjugate base. So let's focus on the conjugate base from the acid-base reaction. Whenever you have a lone pair next to a double bond, you can do resonances. We call this position, actually, we call it a Lilic in organic chemistry. So I do have a lone pair next to a double bond. That tells me that I can push the lone pair inward. You don't want to stop there, because if you stop there, this is the situation you'll have. This carbon right here will have 10 electrons around it instead of 8. You have 5 bonds, so 10 electrons. That is a felony. Someone needs to be jailed. So instead of stopping here, we have to push one more arrow towards the oxygen. This is the resonance sign. We did the resonance lecture before. You will end up with O minus if you do the formal charge calculations, and then you get a double bond here on the other oxygen. So you see, this is resonance stabilization, which means the electrons are delocalized. They are moved around the structure. They are not static. They are not always at one point. So we call this resonance stabilization, and therefore these resonance forms will be weaker bases compared to ethanol, which has 2 carbons like just the acetic acid. This one, there's no resonance stabilization. So the electrons are always found right where the oxygen is, and this conjugate base is stronger base. For that reason, the parent acid, which is ethanol, will be a weaker acid, because it's the conjugate base formed after acid-base reaction is not stable. Stronger bases always come from weaker parent acids. So in this case, acetic acid forms resonance stabilized conjugate base. So it will want to do that, because it knows once it loses the hydrogen, it's going to be stabilized by something, which is resonance in this case. So acetic acid is going to be a stronger acid, because its conjugate base is weaker base. The weaker the conjugate base, the stronger the parent acid. So acidity goes that way. Acetic acid is stronger than ethanol. Let's do another example on the side. Example number 2. This time, let's consider cyclohexanol, an alcohol, versus phenol. Which of these two is more acidic? We do the same thing. We bring a prototype generic base, use the base to take out that hydrogen, and make an anion out of the molecule. So we will end up with this anion out of cyclohexanol, and you will end up with, of course, the conjugate base, the conjugate acid. You will end up with the conjugate acid. So same thing here. Let's take a prototype base that is strong enough to take out that hydrogen. You will get O minus with the double bonds in there, but you're still going to end up with a conjugate acid. Okay, so what do we have here? We have resonance stabilization on the phenoxide. You saw this before in an earlier lesson. On the cyclohexanol conjugate base, there is no resonance stabilization. Like I said, whenever you have a lone pair next to a double bond, call that position where the lone pair is allylic. You expect to push resonance. You want to push the arrow there, and like I said, you don't want to end up with 10 electrons. You don't want to stop here. The pi bond has to give way. This double bond, one is a sigma, one is pi, so one of the bonds will give way. So I'm showing you resonance stabilization of the phenoxide, just one of it. I think you can draw more than 3 resonance structures out of this. It's very, very resonance stabilized. We discussed resonance stabilization in a different lecture. Look for the link below this YouTube video for the other lecture on resonances if you want to refresh. So this is what you'll end up with, and you can draw even more. You can draw even more resonances. So because this is resonance stabilized, it's gonna be the weaker conjugate base of the two. And we say that if the conjugate base is weak, it must have come from a stronger acid. So cyclohexanol is less acidic than the phenol. This one has no stabilization. This one has no resonance. No resonance stabilization for this guy. Okay, so phenol is more acidic than cyclohexanol because the conjugate base is resonance stabilized. Let's look at another factor. The next factor is inductive effect. Let's talk about inductive effect. In this case, we're going to go back to electronegativity. We'll discuss the tendency of an electronegative element present in a molecule pulling electrons towards itself, pulling electron density towards itself. So let's take an example of acetic acid. This guy only has hydrogens. Okay, and then we find another molecule, and then we compare it to one that has chlorines on it, maybe one chlorine for now. We're just substituting one hydrogen with a chlorine, and then one that has 2 chlorines, versus one that has 3 chlorines. Which one is more acidic? Now you can imagine this guy losing the most acidic hydrogen in the molecule. This is the most acidic hydrogen in the molecule. It sits on the more electronegative element compared to these hydrogens, Hydrogen on oxygen is more acidic than hydrogen on carbon. That's the most acidic hydrogen in the molecule. So we will find that we will get this conjugate base when a base takes out that hydrogen, the most acidic hydrogen in the molecule. And you will always get your conjugate acid, of course. Okay, that's from there. And then here we do the same thing. You just take your base that can do this job, removing the most acidic hydrogen on the molecule, which is the one sitting directly on electronegative oxygen. Okay. You will get that conjugate base, and of course you're going to get the acid out of it. So we'll do the same for the 3. Okay, so now let us focus on the conjugate bases, these ones. You'll see that all of them are the molecules, all of them are resonance stabilized. You can push resonance, you can push resonance, you can push resonance. So resonance here is not a major factor because all of them have resonance stabilization. But the difference here is gonna be the difference here is gonna be inductive effect. You see, whenever you have an electron withdrawing group, what it does, it sucks electrons towards itself through bond. So electron density attraction through bond is called inductive effect. And that's because you have a chlorine. And if you have multiple electron withdrawing groups, then you have more of that pool. So the electron density on oxygen is quite reduced. Okay, so in this case, the weakest conjugate base is gonna be this. That's the weakest conjugate base. And I'll tell you again, the weaker the conjugate base, the stronger the parent acid. This one will be the stronger. It's not a strong base, of course. I'm just comparing relatively. This is the stronger conjugate base out of the red ones, So this will be the weakest acid because it lacks those electron withdrawing groups. This only has 1, this has 2, and the last one has 3. This will be the strongest acid. That's how you do it. Based on electronegativity, presence of electron withdrawing groups. Let's look at the last factor, which is, we've done the I, which is inductive effect. Let's look at the last factor, which is the orbital type that goes with hybridization. I'll remind you that with hybridization in organic chemistry, we always consider sp, and we say that sp is more acidic than sp2. We covered this in an earlier lesson, which is more acidic than sp3. So this will be what we'll be basing on. Okay. Remember, we say that the higher the S character or percentage, the higher the acidity. That was our idea. If you look at sp, you only have 2 orbitals. They are hybridized. So S character here is 50%. Here you have 3 things. S character here would be 33.3%. In sp3, the S character will be 25%. The reason is the S orbital is usually the closest to the nucleus. So you can imagine the electrons being attracted so strongly to the nucleus, which contains protons, right? And protons are positive. So the higher the S character, the more close the electrons are to the nucleus of the atom, the more stronger they are attracted and held by the nucleus of the atom, the more acidic it will be. So now, having said that, let's say that you have methane, simple example. Let's compare it to ethene, an alkene. All these hydrogens are sitting on carbons, so electronegativity is not a factor here. And then I'm showing you ethane. Okay, so you have methane falling under the class of alkenes. Then you have ethene falling under the class of alkenes. then you have acetylene, otherwise called ethine, falling under the class of alkyne hydrocarbons. We did hybridization, and we said that you just simply count the electron domains. This carbon here has 4 electron domains, so it has to be sp PP, which is sp3. That's a shortcut. This carbon, or rather this carbon, have 3 electron domains: the single bond, double bond. They are counted each as an electron region, electron domain. So 1, 2, 3, I have to be having spp, so that is sp2 for both of them. And then this one has 2 electron domains. A triple bond is 1 electron domain, a single bond is 1 electron domain. If we had a lone pair, that would be another electron domain. So since I have 2 electron domains, this is sp. So what we are saying is that the CH, the sp CH is more acidic than the sp2 CH, which will be more acidic than the sp3 CH. So acidity increases going to the right, with the ethine being most acidic. That's the idea. Okay. So I hope that helps, and you should be able now to analyze any complex molecule using this simple thought process. See you again for another lesson, and watch out for the important links for your review under this video, under this YouTube video. Bye. Ciao. Bye.